Hello everyone, and welcome. I'm excited to start today's presentation on relation and function. This is the very first slide, and it's our cover slide, so I just want to quickly introduce the topic. The title is Relation and Function, and there may be a subtitle as well. Over the course of this presentation, we will explore what relations and functions are, how they are related, and why they are important in mathematics. So, let's get started and dive into these fundamental concepts. Let's take a quick look at the contents for today's session. We'll start with the learning objectives to set our goals. Then, we'll explore the fundamental concepts of relations and functions, including their types and how they relate to each other. We'll examine the Cartesian product of sets, which is essential for understanding how relations are formed. Moving forward, we'll discuss the domain and range of functions, key components that tell us about the input and output. We'll also cover equivalence relations and various types of relations, highlighting how they help us classify and understand relationships between sets. Then, we'll look at different types of functions, including bijective functions, which have special properties. There will be practice questions to reinforce your understanding, and some activities to actively engage with the material. Overall, this slide provides a roadmap for what we'll be covering, tying everything back to the broader theme of understanding how elements in sets interact through relations and functions. Today, we'll be focusing on the learning objectives for this section. First, I want to emphasize the importance of explaining the key points thoroughly, but in a conversational way. This helps ensure clarity and keeps our audience engaged. Next, we'll highlight the most important concepts, making sure they stand out and are easily memorable. Finally, I'll show you how to connect these points to the overall theme of our presentation, so everything ties together cohesively. Remember, the goal is to make the content accessible and relevant, reinforcing how each part contributes to the bigger picture. Let's start by exploring some fundamental concepts related to functions and relations. First, we'll look at the definition, domain, and range of functions. Understanding these basics is essential because they form the foundation for more advanced topics. The domain is the set of all possible inputs for a function, while the range is the set of all outputs it produces. Next, we'll discuss how to define and find the inverse of functions. This is important because the inverse essentially reverses the mapping of the original function, and identifying it helps us understand the function's behavior better. We'll also cover the concept of equivalence classes of elements. Think of this as grouping elements that are related in a specific way under a relation, which is a key idea when studying how elements are connected. Then, we'll move on to the composition of functions, which is about combining functions so that the output of one becomes the input of another. This operation is powerful because it allows us to build more complex functions from simpler ones. We'll classify functions as injective, surjective, and bijective. These classifications tell us about how functions map elements between sets, particularly whether they are one-to-one, onto, or both. Finally, we'll examine relations and how they can be classified as reflexive, symmetric, and transitive. These properties describe the nature of the relationships between elements. We'll also define what a relation is, along with its domain and range. This sets the stage for understanding how elements relate to each other in various contexts. Overall, these concepts are interconnected and fundamental to mastering the structure and behavior of functions and relations in mathematics. Let's dive into the concept of Cartesian products of sets. Essentially, when we talk about Cartesian products, we're looking at all possible ordered pairs that can be formed by taking one element from each set. For example, if we have set A and set B, the Cartesian product of times B includes every combination where the first element is from A and the second is from B. This idea is fundamental because it helps us understand how different sets interact and combine, which is key in many areas of mathematics and computer science. As we explore these products, keep in mind how they connect to the bigger picture of set theory and how they form the basis for relations and functions. Understanding Cartesian products sets the stage for more complex concepts we'll encounter later. Let's take a closer look at this notation. we have a times b, which is written as a times b, and it represents something called the Cartesian product of the sets A and B. Now, this set contains all ordered pairs, which are written as x, y. The key point here is that for each pair, must come from set A, and y must come from set B, so we're essentially pairing each element of A with each element of B. When we see the notation x, y, A and yb, it means the set of all pairs x, y such that is in A and y is in B. It's a compact way to describe this entire collection of pairs. This concept is fundamental because it helps us understand how sets can be combined to form new structures, especially when dealing with relations and functions. And of course, the Cartesian product is a building block that appears frequently throughout this course. In summary, the Cartesian product gives us a way to systematically pair elements from two sets, which is essential for exploring more complex ideas in set theory and mathematics in general. Now let's take a closer look at these Cartesian product sets. On the left, we have B times A, which consists of all ordered pairs where the first element comes from B and the second from A specifically. These are 4, 1, 4, 2, 4, 3, and similarly for 5 we have 5, 1, 5, 2, and 5, 3. On the right, we see a times B, which flips the order pairs where the first element is from A and the second from B. These are 1, 4, 2, 4, 3, 4, and then for 5, 1, 5, 2, 5, and 3, 5. It's important to notice that the order of the pairs reflects the order of the sets in the Cartesian product. So, B times A pairs elements from B with A, while a times B pairs elements from A with B. Now, if we specify A as the set 1, 2, 3, and B as 4, 5, these examples help us understand how the Cartesian product works with specific sets. It highlights that the pairs are formed by combining each element of one set with every element of the other, respecting the order. This concept is fundamental because it underpins how we think about relations and functions between sets. It also helps us visualize the structure of all possible pairings, which is essential in many areas of mathematics and computer science. So, in essence, these examples illustrate the core idea of Cartesian products, creating ordered pairs by systematically pairing elements from two sets, with the order in the pair reflecting the order of the sets in the product. Let's take a closer look at relations. In this section, we're exploring how different elements or entities are interconnected within the system. Relations are fundamental because they help us understand the structure and the dynamics at play. By analyzing these relationships, we can identify patterns, dependencies, and influences that shape the overall behavior. It's important to highlight that relationships are not just static links. They can be complex and multidimensional. Recognizing these nuances allows us to better interpret the data and make more informed decisions. Throughout this presentation, we've emphasized the importance of understanding connections, and this slide ties directly into that theme. By grasping the key relations, we gain deeper insights into the system's functioning, which ultimately enhances our ability to optimize and innovate. Let's talk about the set of all first elements in a relation, which we call the domain of the relation. This is essentially the collection of all the starting points in our relation. On the other hand, the set of all second elements, often called images, represents the range of the relation. These are the endpoints or outputs associated with each element in the domain. Now, when we define a relation R from a non-empty set A to another non-empty set B, it's important to understand that R is actually a subset of the Cartesian product of A and B, which is written as a times B. This means that every element in the relation is a pair, with the first component coming from A and the second from B. So, in essence, relations are a way to connect elements from one set to another, and understanding the domain and range helps us see exactly what elements are involved and how they relate to each other. This concept is fundamental as we explore how different sets interact through relations in more complex structures. Let's take a closer look at the total number of possible relations from set A to set B. This is given by 2 to the power of pq, where p and q are the sizes of the sets. If we have n, A equal to p, and n, b equal to q, then the number of elements in the Cartesian product A times b is pq. Now consider this example. The set R equals 1, 2, minus 2, 3, 1, 2, 3. This set R is a relation because it connects elements from one set to another. The domain of R, which is the set of all first elements in the ordered pairs, is 1, minus 2, 1, 2. The range, on the other hand, is the set of all second elements, which is 2, 3. What this example illustrates is how relations are formed and how they connect elements across sets. Understanding the size of the sets and how relations are constructed is fundamental to grasping more complex concepts in set theory and relations. A relation on set A means a relation from set A to itself. In other words, it's a subset of the Cartesian product A times A. So, essentially, when we talk about a relation on A, we're looking at certain pairs of elements within A that are related according to some rule or property. This concept is fundamental because it helps us formalize how elements in a set can be connected or associated with each other, which is central to understanding more complex structures like functions, orderings, and equivalence relations. Recognizing that a relation is just a subset of a cross A gives us a clear way to visualize and analyze these connections within the set. Now let's look at the second part. We need to write down the domain, codomain, and range of this relation R. Remember, R is defined as the set of all pairs where y equals x plus 1. Next, for the first part, we're asked to depict this relation visually using an arrow diagram. Think of it as drawing arrows from each element in the domain to its corresponding element in the codomain based on the rule y equals x plus 1. Moving on, we have our set A, which contains the numbers 1 through 6. We will define our relation R from A to A, meaning both the domain and codomain are the same set. As an example, if x is 1, then y is 2. If x is 2, then y is 3, and so on. We'll see how this simple rule creates connections between elements in the set A. This exercise helps us understand how relations work within the same set, and visual tools like arrow diagrams are great for clarifying these connections. By analyzing the domain, codomain, and range, we deepen our understanding of how relations behave, especially when working with finite sets like this one. Let's take a closer look at the domain, which is the set 1, 2, 3, 4, 5. As you can see, these are the input values or the elements that we're considering for our relation. Moving on, the range here is 2, 3, 4, 5, 6, representing the possible output values or the elements that our relation can map to. And finally, the codomain is slightly broader, including 1, 2, 3, 4, 5, 6. This is the set that contains all possible outputs, whether or not they are actually mapped to in our relation. Now the relation R is given as the set of ordered pairs 1, 2, 2, 3, 3, 4, 4, 5, and 5, 6. These pairs show us how each element in the domain is paired with an element in the range, according to the relation. By the definition of the relation, each of these pairs indicates a specific connection between elements of the domain and the range. It's important to understand that these pairs define the relationship explicitly, showing us exactly which elements are related. So, in summary, this slide illustrates how the domain, range, and codomain are structured, and how the relation R explicitly connects each element of the domain to a corresponding element in the range, based on these pairs. This helps us understand the nature of the relation in a clear and organized way. Now, let's take a closer look at the different types of relations. These are fundamental because they help us understand how data points are connected within a database or a system. First, we have one-to-one relations, where a single record in one table is linked to a single record in another. Think of it like a person and their passport. Each person has only one passport, and each passport belongs to only one person. Then, there are one-to-many relations, which are more common. For example, a single customer can place multiple orders, but each order belongs to only one customer. This kind of relation helps us organize data efficiently and reflect real-world scenarios. Next, we have many-to-many relations, which are a bit more complex. They occur when multiple records in one table relate to multiple records in another. An example could be students and courses. Students can enroll in many courses, and each course can have many students. To manage this, we often introduce a junction table. Recognizing these relation types is crucial because they influence how we design databases to ensure data integrity and optimize performance. Throughout this presentation, understanding these relations will help us build more effective and reliable systems. There exists an element x equal to 1 in the set such that the pair 1 is not in the relation R now, remember. The relation R is defined on the set A, which contains the elements from 1 to 14. Specifically, R includes pairs where 3 times x minus y equals 0. So, for example, the pairs are 1, 3, 2, 6, 3, 9, and 4, 12. Notice that this relation is actually not reflexive. Why? Because for a relation to be reflexive, every element in A must relate to itself, meaning each x pair should be in R, but in this case, 1 is not in R, since 3 times 1 minus 1 equals 2, which is not 0. Let me give you a concrete example of a relation that is reflexive. If R consists of pairs like 1, 1, 2, 2, and 4, 4, then it is reflexive because each element relates to itself. In general, a relation R on a set A is called reflexive if, for every element in A, the pair x is in R. So, the key point here is that for reflexivity, all these self-pairs must be present, and if even one is missing, the relation is not reflexive. This concept connects to the overall theme of understanding how relations behave on sets, especially in terms of properties like reflexivity. Let's take a closer look at Activity 1, which is labeled as Step 5. This part of the presentation is really important because it helps us understand the foundational concepts we're working with. I'll explain the key points thoroughly, but I'll keep it conversational so it feels natural and easy to follow. The main idea here is to highlight the most important concepts that connect directly to our overall theme, which is about improving efficiency and effectiveness in our processes. By focusing on these core ideas, we can better see how each activity contributes to our larger goals. Remember, the goal of this activity is not just to complete a task, but to understand the underlying principles that make the process work. This understanding is crucial as we move forward, because it allows us to apply these concepts more effectively in real-world scenarios. So, as we go through this slide, keep in mind how these points tie into the bigger picture, how they support our mission to optimize performance and drive success. Today, we're going to explore how to find the number of reflexive relations that can be defined on a finite set, which we'll call A, that has n elements. The key idea here is to understand what makes a relation reflexive. Essentially, for a relation to be reflexive, every element in the set must be related to itself. That means, for each element in A, the pair where both elements are the same, like has to be included in the relation. So, when we're counting the number of possible reflexive relations, we need to consider that all these self-related pairs are fixed. They must be present. The question then becomes, what about the other pairs? These are the pairs where the two elements are different, like B. With a not equal to B for each of these pairs, we have the freedom to include it or not, since their inclusion doesn't affect the reflexivity condition. Now, since there are n elements, the total number of pairs in the Cartesian product times A is n squared. Out of these, n pairs are the diagonal pairs where the elements are the same, and these are fixed. They must be present for the relation to be reflexive. The remaining n squared minus n pairs are the off-diagonal pairs, where the elements are different. For each of these off-diagonal pairs, we have two choices, include it or not. Putting it all together, the total number of reflexive relations on set A is 2 raised to the power of the number of these off-diagonal pairs. That is, 2 to the power of n squared minus, and this formula captures all the possible ways we can define reflexive relations on a finite set with n elements, considering that the diagonal pairs are fixed and the off-diagonal pairs are optional. Now, moving on to the materials you'll need for this project. You'll want some grid paper, which is perfect for creating precise and organized designs. White paper is also essential, especially if you're planning to add color or details later on. Don't forget glue and scissors. They're fundamental for assembling and cutting out your pieces. Having these materials ready will make the process smoother and more enjoyable. Remember, the key is to gather everything beforehand so you can focus on being creative without interruptions. These basic supplies are the foundation for bringing your ideas to life, fitting perfectly into our overall theme of hands-on, practical learning. Now let's consider a 4x4 grid and see how we can fill it based on different sets. For example, if we take A as x1, x2, we can list all the possible reflexive relations that can be formed on this set. Similarly, for a set with 3 elements like x1, x2, x3, we'll do the same. And for just one element, say x1, we'll consider the possible relations as well. To visualize these, we'll paste these grids onto our activity sheet. Next, I want you to think about how many such relations exist for each case. For 2 elements, there are a certain number of reflexive relations, and this number increases as we add more elements. Now, to better understand these relations, take a piece of grid paper and cut out squares of sizes 2x2, 3x3, and 4x4. These different-sized grids help us visualize the possible relations on sets with different numbers of elements. The key idea here is that the structure of these grids allows us to systematically explore all possible reflexive relations, and counting these helps us understand the broader concept of relations in set theory. Now, moving on to the application of this concept, we see that this activity can actually be extended to explore the number of symmetric relations on a finite set, which we'll call A if this set A has n elements. Then an interesting question arises. How many reflexive relations can we define on this set? The answer to that is something we can determine mathematically. It's important because it connects the idea of relations to broader combinatorial concepts. Understanding this helps us see the bigger picture of how relations behave and how many different types we can construct based on the properties we want, like symmetry or reflexivity. So, as we wrap up this point, think of it as a stepping stone towards grasping the overall structure and variety of relations in set theory, which is a fundamental part of understanding how different elements relate to each other within a set. Now, let's take a closer look at the different types of relations. When we talk about relations in this context, we're referring to how different data entities are connected or associated with each other. These relationships are fundamental because they help us organize and retrieve data efficiently. There are several key types of relations to be aware of. The first is the one-to-one relation, where a single entity in one table is related to a single entity in another table. Think of it like a person and their passport. Each person has one passport, and each passport belongs to one person. Next, we have the one-to-many relation, which is quite common. Here, a single entity in one table is related to multiple entities in another table. For example, a single customer can place many orders, but each order is linked to just one customer. Then, we also encounter the many-to-many relation, where multiple entities in one table relate to multiple entities in another. For instance, students and courses. Students can enroll in many courses, and each course can have many students. Managing this type of relation often involves a junction table to keep things organized. Understanding these different relation types helps us design databases that are both efficient and logical, supporting the integrity of our data and making future data management much smoother. This is a crucial step in ensuring our overall data architecture is solid and scalable. Let's look at this example. There exists an element x equal to 1 and an element y equal to 3 in the set A, such that the ordered pair 1, 3 is in the relation R. However, the reverse pair 3, 1 is not in R now, recalling the set R is defined as R equals 1, 3, 2, 6, 3, 9, 4, 12. We see that this relation is not symmetric. A relation on set A is considered not symmetric if we can find at least one pair x, y in a where x, y is in R, but the pair y, x is not in R. It's important to note that in some cases, like the relation R equals 1, 1, 1, 3, 2, 2, 3, 1, 3, 3. If 1, 3 is in R, then 3, 1 must also be in R for the relation to be symmetric. For example, consider a relation R on a equals 1, 2, 3, where R is defined as the set of pairs x, y such that x plus y is even. This relation is symmetric because if x, y is in R, then y, x will also be in R due to the commutative nature of addition. In summary, a relation is symmetric if whenever is related to y. Then y is also related to x. This concept is crucial because it helps us understand the nature of relations, whether they are mutual or one-sided, and how they behave within the set. Let's take a closer look at the different types of relations. When we talk about relations, we're essentially exploring how various data elements connect or interact with each other. There are several key types to understand, each playing a crucial role in organizing and making sense of data. First, we have one-to-one relations, where a single element in one set is related to a single element in another set. This is straightforward and often used for unique pairings. Next, we have one-to-many relations, which are quite common. They occur when one element in a set connects to multiple elements in another set, like a single customer placing multiple orders. Then, there's many-to-many relations, which are a bit more complex. They involve multiple elements in one set relating to multiple elements in another. This often requires a junction or associative table to manage the connections effectively. Understanding these relation types helps us design better databases and ensures data integrity across systems. Connecting this to our overall theme, recognizing the different relation types is fundamental for building efficient, reliable data models that support robust information systems. So here we see an example where there exist elements equals 1, y equals 3, and z equals 9, all belonging to set A now. In this case, the ordered pairs 1, 3, and 3, 9 are both part of the relation R. However, the pair 1, 9 is not in R. This illustrates that the relation R is not transitive. Remember, the set A includes numbers from 1 up to 14, and the relation R is defined as all pairs x, y, where 3 times x minus y equals 0. In this example, the pairs 1, 3, 2, 6, 3, 9, and 4, 12 are in R, but crucially, the relation fails to be transitive because even though 1, 3, and 3, 9 are in R, the pair 1, 9 isn't. Now, to clarify what makes a relation transitive, it means that if x is related to y and y is related to z, then must be related to z as well. So, in formal terms, if x, y, and y, z are in R, then x, z should also be in R for the relation to be transitive. Here's a quick example. Consider the relation on the set A equals 1, 2, 3, where the relation R includes pairs like x, y if x plus y is even. In this case, R turns out to be transitive because whenever you have x, y, and y, z in R, the pair x, z will also satisfy the relation. To sum up, the key takeaway is that transitivity depends on this chain of relations holding true consistently. If it breaks at any point, meaning you have x, y, and y, z, but not x, z, then the relation is not transitive. And that's an important concept to understand as we analyze different relations in set theory. Let's take a closer look at the concept of an equivalence relation. An equivalence relation is a special kind of relation that helps us group objects into categories that are considered equivalent in some sense. To qualify as an equivalence relation, 3 key properties must be satisfied: reflexivity, symmetry, and transitivity. Reflexivity means every element is related to itself, which makes sense because an object should be equivalent to itself. Symmetry means if one element is related to another, then the second should also be related to the first. And transitivity ensures that if an element is related to a second, and that second is related to a third, then the first should also be related to the third. These properties together allow us to partition a set into equivalence classes, where all members of a class are considered equivalent. This concept is fundamental because it provides a structured way to understand how objects relate and group together based on shared properties. It ties into the overall theme of understanding relationships and classifications within mathematical structures. Let's take a closer look at this slide. First, we see the notation that the union of all the sets AJ equals X, which means that the collection of these subsets completely covers the set X additionally. These subsets are pairwise disjoint, as indicated by the statement that AI intersect AJ is empty whenever I is not equal to J. This implies that no element belongs to more than one subset, and each element of X belongs to exactly one of these AI. Now, an important point here is that no element of one AI is related to any element of another AJ when I is not equal to J. In other words, these subsets are separated in terms of the relation we're discussing. These subsets are called equivalence classes, and what's key is that within each AI, all elements are related to each other. This idea of equivalence classes helps us understand how a relation partitions a set into distinct, non-overlapping parts. When we have an arbitrary equivalence relation R on set X, it divides X into these mutually disjoint subsets, which we call partitions or subdivisions. Finally, for a relation R to be considered an equivalence relation on a set A, it must satisfy three properties. It must be reflexive, meaning every element relates to itself. Symmetric, meaning if one element relates to another, then the second relates back to the first. And transitive, meaning if an element relates to a second, and that second relates to a third, then the first relates to the third. Connecting all these points, the overall idea is that an equivalence relation creates a natural partition of the set into equivalence classes, which are the building blocks for understanding the structure of the set in terms of the relation. Now let's take a closer look at this relation R, which is defined as R equals the set of all pairs, a B, where 2 divides the difference, a minus B. Essentially, this means that R relates two integers if their difference is an even number. What's important here is to show that this relation R is an equivalence relation on the set of integers. Remember, an equivalence relation must be reflexive, symmetric, and transitive. For example, the equivalence class of an element X, denoted by X, includes all integers that are related to X under this relation. So, in this case, X would contain all integers that differ from by an even number. Highlighting these key points helps us understand how this relation partitions the set of integers into distinct equivalence classes, which is a fundamental concept in understanding the structure of sets under relations. This ties back to our overall theme of exploring how relations define partitions and organize elements into meaningful groups. Let's consider two elements, A and B, both belonging to the real numbers, and similarly B and C also in the real numbers. If we look at the differences, A minus B and B minus C, both are divisible by 2. This is a key point because it shows that the relation R is transitive. Now recall that R also includes the union of even and odd integers, which together make up the entire set of integers, Z specifically. The even integers are represented by the set E, which is 0 and all multiples of 2, like plus or minus 2, plus or minus 4, and so on. The odd integers are in set O, which includes plus or minus 1, plus or minus 3, etc. Next, let's examine what happens if a B is in R since 2 divides a minus B. We can write a minus B as 2 times some integer m from this. It follows that B minus A equals 2 times negative m, which is also divisible by 2. Therefore, the pair B A is also in R, confirming that R is symmetric. Additionally, all odd integers are related to 1, because pairs like 1, plus or minus 3, plus or minus 5, etc., are in R. Similarly, all even integers are related to 0, since pairs like 0, plus or minus 2, plus or minus 4, etc., are in R. Finally, when we look at the difference A minus C, it can be expressed as the sum of A minus B and B minus C. Since both are divisible by 2, their sum is also divisible by 2. This demonstrates that R is transitive, as the difference between A and C is divisible by 2. And importantly, for any M in Z, A minus A equals 0, which is divisible by 2, so R is reflexive. This example really highlights how the relation R combines properties like symmetry, transitivity, and reflexivity, giving us a solid understanding of its structure within the set of integers. Let's look at example 3. Here, we're diving into a practical scenario that illustrates the core concepts we've been discussing. As we go through this, pay attention to how the key points come together to reinforce the overall message. It's important to see how these ideas connect and apply in real-world situations. This example highlights the significance of understanding the underlying principles and adapting them to different contexts. Remember, the goal is to grasp not just the theory, but also how to implement it effectively. So, as we analyze this example, think about how it ties back to the broader themes of the presentation and how it can inform your own practices. All right, let's look at example 3. When I say do as HW, I mean we should follow the homework or practice instructions carefully. In this slide, I want to emphasize the importance of applying what we've learned through real-world examples. Think of this as a way to solidify your understanding by actively engaging with the material. So, for this content, focus on thoroughly explaining the key points, but in a friendly, conversational way. Make sure to highlight the most critical concepts, because those are the ideas that will stick with you. And of course, always try to connect these points back to the overall theme we're discussing in this presentation. This helps keep everything cohesive and reinforces how each example relates to the bigger picture. So, remember, do as HW, and apply these principles thoughtfully and actively. So here we see that the relation R is actually not transitive. To understand this better, let's consider specific examples. Suppose we take A equals 10, B equals 5, and C equals 3. Now, according to our relation R, we have that 10, 5 is in R, and also 5, 3 is in R. However, when we look at the pair 10, 3, it turns out that this is not in R. This example clearly demonstrates that even if O is related to B, and B is related to C, it doesn't necessarily mean that A is related to C. That's the key point here. Transitivity does not hold for this relation. Understanding this helps us see the importance of checking the properties of relations carefully, especially when analyzing how elements are connected within a set. It also reminds us that not all relations are transitive, which can have significant implications depending on the context of our study. So R is symmetric. This means that the matrix R is equal to its transpose, which is a key property in many mathematical and practical applications. When a matrix is symmetric, it simplifies analysis and computations, especially in areas like optimization and linear algebra. Moving on to solution 4, this builds on that concept and offers a specific approach or insight related to the symmetry of R throughout this presentation. We're seeing how these properties influence the behavior and solutions of the systems we're studying. Symmetry often leads to more elegant and efficient solutions, which is why it's such an important aspect to highlight. Let's take a closer look at functions. Functions are essentially the building blocks of programming. They allow us to organize our code into reusable, modular pieces. This way, instead of rewriting the same code over and over, we can just call a function whenever we need it. Functions help us keep our code clean and manageable, especially as projects grow larger and more complex. They also make debugging easier because if something goes wrong, we can focus on a specific function rather than the entire program. In the context of our overall theme, understanding functions is crucial because they enable us to write efficient, scalable, and maintainable code. They are fundamental to good programming practices and essential for developing robust applications. Let's consider the sets A and B here. Set A contains the elements 1, 2, 3, and 4, while set B includes the elements of B, C, D, and E. Now, we have these rules, F1, F2, F3, and F4, which associate elements of B to elements of A, as shown in the figures. Our goal is to identify which of these rules actually define functions from A to B. Remember, when we say an element in A is associated with an element B in B, we call B the F-image of A, and conversely, A is called the preimage of B. We write this relationship as B equals F of A, or B equals F, A's. Now, a function from set A to set B must assign exactly one element of B to each element of A. In other words, every element in A has to have a single, well-defined image in B. So, as we analyze each rule, Our task is to check whether each element in A is mapped to one and only one element in B. If a rule assigns multiple images to a single element in A, it's not a function. If it assigns none, then it's incomplete. The key point here is understanding that a function must provide a unique output in B for every input in A. This ensures the relationship is well-defined and consistent, which is fundamental to the concept of functions in mathematics. Let's take a closer look at this slide. Here, we see a sequence of figures labeled from 1 to 4. These figures are represented as F1, F2, F3, and F4. The numbers 1, 2, 3, and 4 are clearly marked alongside each figure, indicating their order or relationship. What's interesting here is how these figures might connect to the overall concept we're discussing, perhaps illustrating a process, a progression, or different states. The key point to remember is that each figure plays a role in helping us visualize the sequence or structure we're analyzing. By examining these figures carefully, we can better understand how the components relate to each other, which is essential for grasping the bigger picture. So, as we move forward, keep these figures in mind. They serve as a visual aid to reinforce the concepts we've been exploring throughout this presentation. Let's analyze these functions to understand why they are or aren't functions. First, looking at F3, we see that it is a function because each element in set A has a unique image in set B. This means that for every input, there's exactly one output, which is the key characteristic of a function. Now moving to F2, this one is not a function. We can see that the element 3 in set A does not have a unique image in set B. In fact, it might be missing an image or mapped to more than one, which violates the rule that each input must have exactly one output. Finally, for F1, it's also not a function. The reason is that there's an element, specifically 2 in set A, which isn't mapped to any element in set B at all. So again, this breaks the fundamental rule that every element in the domain must have an image. In summary, the key idea here is understanding what makes a relation a function. Each element in the domain must be mapped to exactly one element in the codomain. Any deviation from this, like missing images or multiple images, means it's not a function. Let's talk about the domain of a function. The domain is essentially all the possible input values, or x values, for which the function is defined. It's important because it tells us where the function makes sense and can give us meaningful outputs. When we're analyzing a function, identifying the domain helps us understand its limitations and where it applies. Sometimes the domain is all real numbers, but other times it might be restricted due to square roots, denominators, or other constraints. Recognizing these restrictions is key to fully understanding the behavior of the function. Connecting this to our overall theme, knowing the domain allows us to correctly interpret and graph functions, ensuring we're working within their valid ranges. Let's look at this slide. When we have a function, which we write as f, a right arrow b, the set A is called the domain of f. This is essentially the set of all the inputs or the starting points for our function. Now, on the other hand, the set B is known as the codomain of f. The codomain includes all possible outputs that the function could potentially produce, even if not all of them are actually attained. Understanding the difference between the domain and codomain is really important because it helps us clarify what values we're starting with and what values we're aiming at with our function. This distinction will come in handy as we explore more about how functions behave, especially when we talk about actual outputs versus potential outputs. So, to sum up, the domain is about where our function begins, what inputs are allowed, and the codomain is about the range of possible outputs, which sets the scope for what the function can produce. This foundational understanding will support everything else we learn about functions and their properties. Let's talk about the range of a function. The range essentially tells us all the possible output values that a function can produce. When we analyze a function, understanding its range helps us see what values the dependent variable can take based on the input values. This is important because it gives us a complete picture of how the function behaves. For example, if we're working with a quadratic function, its range might be limited to all values greater than or equal to a certain minimum or less than or equal to a maximum, depending on its graph. Recognizing the range also helps us determine the domain when working backwards. By knowing what outputs are possible, we can better understand what inputs are valid. Overall, the range is a key concept that ties into understanding the full behavior of a function, which is essential as we analyze and interpret various types of functions throughout this course. Let's take a closer look at this slide. The range of the function is a set that includes the elements b, c, d. Now, the codomain is given as b, which is the set where the output values of our function are taken from. The domain, on the other hand, is a, which is the set of all input values for our function. From the adjoining figure, we can see that f is a function from a to b. This means that for every element in the domain, a, the function assigns exactly one element in the codomain b. Now, an important concept here is the set of all the f images, which is called the range of f. We denote this as f, a, meaning it's the set of all outputs that the function actually produces from the inputs in a. Understanding the range helps us see the actual outputs a function can generate within its codomain. It's a crucial idea because it tells us about the behavior and the reach of the function within the larger set B. So, in summary, the range is the collection of all images of the domain elements under the function, giving us a clear picture of what the function can produce. This concept ties back to the overall theme of understanding how functions map inputs to outputs and their significance in mathematical analysis. Let's take a closer look at the different types of functions. Functions can be categorized in various ways, but understanding their key types helps us grasp how they work and how we can utilize them effectively. The main types include linear functions, quadratic functions, polynomial functions, rational functions, exponential functions, and logarithmic functions. Each of these has unique characteristics that make them suitable for modeling different real-world situations. Recognizing these types allows us to select the right function for a specific problem, which is essential as we continue exploring more complex concepts. By understanding the fundamental differences among these functions, we build a strong foundation for analyzing and interpreting data in various contexts. Let's talk about what it means for a function to be 1-1, or an injection. When we say a function f, a right arrow b is 1-1, we're saying that different elements in the domain set A must map to different elements in the codomain set B. In other words, if you pick any two elements O and B in A, and they are not the same, then their images under the function f a and f b must also be different. This can be expressed in two equivalent ways. First, f is 1-1 if whenever O and B are in A and O is not equal to B, then f a is not equal to f b. Alternatively, we can say that if f a equals f b, then A must be equal to B. This second way highlights that the function never collapses different inputs into the same output. Understanding this property is crucial because it ensures that the function preserves distinctness. In the context of our overall theme, knowing whether a function is injective helps us analyze how information is transferred or preserved through the mapping from A to B. It's a fundamental concept that underpins many other ideas in mathematics and helps us understand the structure of functions more deeply. Here we see a function f from set A to set B, and this function is 1-to-1 or injective. That means each element in A maps to a unique element in B, with no two elements in A sharing the same image in B. To make this clearer, let's look at this example table. On the left, we have elements of A B, C, D, and on the right, their images in B, 1, 2, 3, 4, and then a 5. What's important here is that each element in A is paired with a distinct element in B, so if I pick any two different elements in A, say O and B, their images, 1 and 2, are different. This is the hallmark of an injective function. It's also crucial because it helps us understand the structure of functions and how they relate elements between sets without overlaps in the images. This concept ties into the broader theme of understanding how functions behave, especially when we're trying to establish 1-to-1 correspondences or explore concepts like invertibility. Recognizing these injective functions allows us to analyze and construct more complex functions with confidence that each input has a unique output. Let's talk about what it means for a function from set A to set B to be one-to-one, or injective. A function is not one-to-one if there are at least two different elements in A, say x1 and x2, such that x1 is not equal to x2. But when you apply the function, they both map to the same element in B. In other words, different inputs produce the same output, which breaks the one-to-one condition. Next, we introduce the notation for the sizes of sets A and B if we let n, A equal m, and n, B equal n. Then the number of one-to-one functions from A to B can be calculated using permutations, specifically P, N, M. This counts how many ways we can assign distinct images in B to elements in A without repetition. Finally, it's important to note that for these one-to-one functions to exist, the size of A must be less than or equal to the size of B. That is, n. A should be less than or equal to n, B. Otherwise, it's impossible to assign unique images to each element in A without overlaps. This concept ties back to our overall theme of understanding how the structure and size of sets influence the types and number of functions we can define between them. Let's look at this example. The function f from the real numbers to the real numbers, defined by fx equals x squared. Now, an important point here is that this function is not one-to-one. Why? Because if we take -1 and 1, they are clearly not equal, so -1 is not equal to 1. But when we evaluate the function at these points, both give us the same value. F minus 1 equals 1, and F 1 also equals 1. This illustrates a key concept. Even though two different inputs, and 1 produce the same output, the inputs themselves are different. Therefore, the function is not one-to-one or injective. Understanding this distinction is important because it helps us see how functions can behave differently with respect to their inputs and outputs. In the bigger picture, recognizing whether a function is one-to-one or not is crucial for understanding its invertibility and how it behaves across its domain. So, in other words, a function, which we denote as f, from set A to set B, is called onto, or surjective, if for every element B in B, there is at least one element O in A such that when we apply the function to A, we get. Essentially, this means that the function covers the entire set B. Every element in B has a pre-image in A. To put it simply, a function f from A to B is onto if every element of B is an image of some element. In A, you can think of the range of the function as the set of all outputs it produces. And for an onto function, this range is actually equal to the entire codomain, which is B itself. This idea of onto functions, also called surjective functions, is fundamental because it ensures that the function is covering its entire target set. This concept ties into the broader theme of understanding how functions map elements from one set to another, and whether they do so completely or leave some elements out. Recognizing whether a function is onto helps us understand the extent of its coverage and its role in various mathematical contexts. So let's look at this statement. If the function f is onto, then its range is actually equal to its codomain. In other words, being onto means that every element in the codomain has a preimage in the domain. To make this clearer, let's consider this simple example table here. On the left, we have elements in the domain, labeled A, which are a B and C. On the right, we have elements in the codomain labeled B, which are 1, 2, and 3. In this case, the function maps A to 1, B to 2, and C to 3. Since each element of the codomain is covered by some element in the domain, this function is onto. This is a key point because it highlights that the range, the actual outputs we get from the function, is the entire set of B, the codomain. Understanding this relationship helps us see that an onto function essentially covers the entire target set, making the range equal to the codomain. This concept is fundamental when studying functions, especially in understanding their behavior and properties across different mathematical contexts. Let's talk about what it means for a function from set A to set B to be onto, or surjective. A function, which we write as f from A to B, is not onto if there exists at least one element in B that has no preimage in A. In other words, if you pick a particular element in B, and you find that no matter what you look at in A, you can't find an element that maps to that B element, then the function is not onto. Now, to define onto functions properly, a key point is that the size of set A, which is NA, must be greater than or equal to the size of set B, NB. This makes intuitive sense because if O is smaller than B, it's impossible for the function to cover all elements in B, so it can't be onto. Remember, the main idea here is that for a function to be onto, every element in B must be hit by at least one element in A. If there's even one element in B that's left out, the function falls short of being onto. This concept ties back to our overall theme of understanding how functions map elements between sets, and the importance of the relationship between the sizes of those sets. Here, we see that the function f is not onto, and the reason for that is there exists an element, specifically 4 in set B, that doesn't have a preimage in the domain. So, in other words, no element in our domain maps to this 4. This example really helps illustrate what it means for a function to be onto or surjective. When a function is onto, every element in the codomain has at least one preimage. But in this case, since 4 has no preimage, the function falls short of being onto. This kind of example is useful for understanding the importance of checking whether every element in the codomain is actually hit by the function. Let's explore how to determine if a function is onto. First, we want to obtain the value of in terms of y. To do this, we start by setting y equal to f, x. The goal is to express explicitly as a function of y. Now, if we can find some y in the codomain B for which does not exist in the domain A, that is, we can't find an x in A that maps to that y, then we conclude that the function is not onto. This is a crucial point because an onto function, or surjective function, must cover every element in the codomain. Next, after obtaining in terms of y, we need to verify that this x actually exists within the domain A for every y in B. We begin this process by choosing an arbitrary element y in B, and then solving for x. There are two methods to check if the function is onto. Method 1 involves finding the range of the function by setting f, x, equal to y and solving for x if, for every y in B, we can find a corresponding x in A, then the function may be onto. Method 2 simplifies this process. If the range of the function equals the entire codomain B, meaning every element in B has a preimage in A, then we can directly conclude that the function is onto. To summarize, the key steps are: first, express in terms of y. Second, verify that for every y in B, the corresponding x exists in A. And finally, confirm that the range covers all of B. If all these conditions are met, then the function is onto. Let's now talk about bijective functions. A bijective function is a special kind of function that is both injective and surjective. This means that every element in the domain maps to a unique element in the codomain, and every element in the codomain is covered by the function. In other words, there are no duplicates in the mapping, and nothing in the codomain is left out. This concept is really important because it allows us to establish a perfect one-to-one correspondence between sets. When a function is bijective, we can confidently say that the two sets have the same size or cardinality. Understanding bijective functions helps us grasp the idea of invertibility, since a bijective function always has an inverse function that undoes the original mapping. This plays a critical role in many areas of mathematics, including set theory, algebra, and beyond. So, in the broader context of our presentation, bijective functions are fundamental because they allow us to compare and relate different sets in a precise and meaningful way. Here, we see that a function f from A to B is a bijection. This means that for every element y in B, there is a corresponding element in a such that f of x equals y. In other words, the function covers the entire set B without leaving any elements out. Additionally, the function is one-to-one, which is expressed by the condition that if f of x equals f of y, then must equal y. This ensures that no two different elements in a map to the same element in B when a function is both one-to-one and onto, meaning it hits every element in B and assigns each element in a unique image. We call it a bijection. This concept is fundamental because it establishes a perfect pairing between elements of A and B, which is crucial in understanding how different sets relate to each other within the broader context of functions. To define a bijective function from set A to set B, a key point is that the two sets must have the same number of elements. This is expressed as n of A equals n of B, meaning they have the same cardinality. When this condition is met, every element in A can be paired uniquely with an element in B, ensuring a one-to-one correspondence. Now, if both sets have n elements, the number of possible bijective functions between them is n factorial. This factorial represents all the different ways we can pair up elements from A to B without repetition or omission. These concepts are central because they connect the idea of bijections to the size of the sets, which is fundamental in understanding how functions behave between finite sets. Overall, recognizing when a bijection exists and how many such functions there are helps us understand the structure and relationship between different sets in mathematics. Let's look at this example to see how the concepts we've discussed come together in a real-world context. I'll walk you through the key points thoroughly, but in a conversational manner. As we go, I'll highlight the most important ideas to reinforce their significance. Connecting these points to the overall theme of our presentation, you'll see how they illustrate practical application and deepen our understanding. Remember, the goal here is to make these ideas relatable and memorable. So think of this as a way to bring the theory to life with a concrete example. Let's talk about invertible functions. A function, which we can write as f from x to y, is considered invertible if there's another function, g from y back to x, that essentially reverses what f does. More specifically, g composed with f written as gof should give us the identity function on x, meaning it takes any element in x and brings it right back to itself. Similarly, f composed with g, written as fog, should be the identity function on y. In this case, g is called the inverse of f, and we denote it as f to the minus 1 or f minus 1. The key idea here is that invertible functions have this perfect undo capability. They can be reversed by another function. This concept ties into the broader theme of understanding functions that are reversible and how that impacts our grasp of structure and symmetry in mathematics. So, whenever you see a function that has an inverse, you know it's special. It's like a perfect match, allowing us to go back and forth seamlessly between the two sets. If the function f is invertible, then it must be both one-to-one and onto, meaning it uniquely maps each element in the domain to a unique element in the codomain, and every element in the codomain is hit by some element in the domain. Conversely, if a function is one-to-one and onto, then it has an inverse function. This inverse essentially undoes the original mapping, which is why being both injective and surjective is equivalent to invertibility. These concepts are fundamental because they connect the idea of being able to reverse a function with how well it covers its entire range without overlaps. Understanding this relationship is key as we explore the properties and applications of functions in different contexts. Let's look at this example to see how it all comes together. Here, we focus on illustrating the key concepts we've discussed so far. It's important to understand how these ideas translate into real-world applications. By examining this example, we can better grasp how the principles we've covered are applied practically. Remember, the goal is to connect the dots between theory and practice, reinforcing the overall theme of the presentation. So, as we go through this, keep in mind how these points tie into the bigger picture we've been building throughout. Now, let's move on to some questions for practice. These are designed to help reinforce the key points we've discussed so far. As we go through them, I encourage you to think critically about how the concepts connect to the overall theme of this presentation. Remember, the goal here is to deepen your understanding and ensure you're comfortable applying these ideas in real-world situations. So, take your time with each question, and don't hesitate to revisit any part of the material if you need a quick refresher. This practice will be an important step in solidifying your grasp of the content we've covered. Let's take a closer look at the relation R defined on the set of natural numbers. For any two numbers n and m in n, we say that n are m if, when divided by 5, both leave a remainder less than 5. That is, their remainders are 0, 1, 2, 3, or 4. Now our goal is to show that this relation R is an equivalence relation. To do that, we need to verify three properties: reflexivity, symmetry, and transitivity. Reflexivity means that every natural number n should be related to itself, which makes sense here since dividing n by 5 leaves some remainder less than 5. Symmetry requires that if n are m, then m are n, which is also true because the division remainders are independent of the order. And transitivity asks that if n are rem and m are rel, then n are rel, which holds because the remainders are consistent within these classes. Once we've established these properties, we can identify the equivalence classes, which turn out to be the sets of natural numbers sharing the same remainder when divided by 5. These classes are pairwise disjoint, meaning they don't overlap, and they partition the set of natural numbers into 5 distinct subsets. This example nicely illustrates how relations can organize elements into meaningful groups based on shared properties. Welcome to this slide on the composition of functions. Here, we're focusing on how functions can be combined to form new functions. This concept is really fundamental because it shows how complex operations can be built from simpler ones. When we talk about the composition of functions, we're essentially looking at how one function's output becomes the input for another. It's like chaining functions together. Think of it as a sequence of steps where each step depends on the previous one. Understanding this helps us see the bigger picture in mathematics and computer science, where combining functions efficiently is key to solving problems. The key point to remember is that the composition of functions allows us to create more complex transformations by linking simpler functions. This idea ties back to the overall theme of building systems from basic components, which is a recurring concept in many areas of math and beyond. Now let's talk about what we call the composition of two functions, which is often written as GOF, x. This means that we're applying the function g to the result of applying f to x. In other words, instead of applying just one function, we're chaining them together. When we say that GOF x equals g of fx, we're emphasizing that for every in our set A, the output is obtained by first applying f to x and then applying g to that result. It's important to note that we have two functions here, f, which maps from set A to set B, and g, which maps from set B to set C. The composition, GOF, then gives us a new function that maps directly from A to C. This concept is fundamental because it shows how functions can be combined to create new functions, and it plays a key role in understanding more complex transformations and processes in mathematics. So the main takeaway is that the composition, GOF, is defined by applying f first, then g, and it's a powerful way to build new functions from existing ones. To properly define the composition of functions, specifically the fog, we need to ensure that the range of g is a subset of the domain of f. This means that every output of g must be an input for f, so the composition makes sense mathematically. Similarly, when we're talking about the composition of GOF, the condition flips slightly. We need the range of f to be a subset of the domain of g. This guarantees that each output from f can be properly fed into g, allowing the composition to be well-defined. These points are crucial because they highlight how the relationship between the domain and range of functions determines whether their compositions are valid. Understanding these conditions helps us see how functions connect and interact within larger mathematical structures, which is fundamental as we explore more complex concepts in this presentation. Now let's look at this example to understand how to find the compositions of functions. We have a function f from R to R, defined by f of x equals x squared. Then, there's another function g from R to R, defined by g of x equals 2x plus 1. Our goal here is to find the compositions of these functions, specifically fog and GOF. First, let's think about what fog means. It means we apply g first, then f, so we take x, plug it into g, and then take that result and plug it into f. Similarly, GOF means we apply f first and then g we start with x, plug it into f, and then take that result and plug it into g. This process helps us understand how these functions interact when composed, which is a key concept in understanding more complex functions and their behaviors. So, by working through these examples, we're strengthening our ability to manipulate and understand function compositions, which is essential in many areas of mathematics and its applications. Let's take a closer look at this slide. Clearly, in this case, fog is not equal to GOF. Now, to understand why, let's examine the functions involved. We have g of f of x, which is written as g composed with f, and that equals g of f of x. Substituting, we get g of x squared, since f of x is x squared. Applying g to that, we get 2 times squared plus 1. On the other hand, we have f of g of x, which is f composed with g that equals f of g of x, which is f of 2x plus 1. When we apply f to 2x plus 1, we square that entire expression, resulting in 2x plus 1 squared. Expanding that, we get 4x squared plus 4x plus 1. Now, an important point to note here is that the range of f is a subset of the domain of G. And conversely, the range of G is a subset of the domain of f because of this. Both compositions, fog and GOF, are well defined. The key takeaway is that even though both compositions are defined, they are not equal in this case. This example highlights that composition is not necessarily commutative, meaning the order in which we compose functions matters. Understanding this concept is crucial as we explore more complex function interactions in this presentation. It is not necessary that both fog and GOF exist, and if they do exist, they may not be equal. What I mean by this is that in many systems, we can't assume that both elements will always be present at the same time. Sometimes, one might exist without the other, and even when both are present, there's no guarantee that they are equal or comparable in any meaningful way. This highlights the importance of understanding the conditions under which these elements appear and how they relate, or don't relate, to each other within the broader context of our discussion. Let's now look at finding the compositions of these functions, specifically g composed with f and f composed with g, if they exist. Recall that g is defined by the set of ordered pairs, 2, 3, 5, 1, 1, 3, and f is given by 1, 2, 3, 5, 4, 1. To find g composed with f, or g of f, we need to see where f takes an input and then see where g takes that output. So, for each element in the domain of f, we look at its output and then check if g has that as an input. For example, f takes 1 to 2. Now, does g take 2 as an input? Yes, g takes 2 and maps it to 3. Similarly, f takes 3 to 5. Does g take 5 as an input? Yes, g maps 5 to 1. Next, f takes 4 to 1. Does g take 1 as an input? Yes, g maps 1 to 3. So g composed with f includes the pairs where the output of f is in the domain of g, leading us to the pairs 1, 3, 3, 1, and 4, 3. Now, let's consider f composed with g, or f of g. We do the same process. Look at g's outputs and see if they are in the domain of f. G takes 2 to 3, but f's domain is 1, 3, 4. Since 3 is in the domain of f, we check where g takes 2, which is 3, and f takes 3 to 5. Similarly, g takes 5 to 1, but 1 is in the domain of f, and f takes 1 to 2. Finally, g takes 1 to 3, and as before, f takes 3 to 5. So f composed with g includes the pairs 2, 5, 5, 2, and 1, 5. In summary, we've identified these compositions, provided they exist, by carefully tracking the outputs and inputs through the functions. This approach helps us understand how combining functions works in a set theoretic context. Let's look at these examples of functions and their compositions. First, we have fog, which is defined as the set of ordered pairs 2, 5, 5, 2, 1, 5. Similarly, GOF is given as 1, 3, 3, 1, 4, 3. Now notice that the range of the function f, which is 2, 5, 1, matches the domain of g, which is 2, 5, 1. This means that the composition G of f, or GOF, exists because the output values of f are suitable as input values for G. On the other hand, the range of G, which is 3, 1, is the set of outputs of G. The domain of f, however, is 1, 3, 4. Since the range of G overlaps with the domain of f, the composition f of G, or fog, exists as well. The key takeaway here is understanding how the range of one function relates to the domain of the other when composing functions. If they align properly, the composition is well defined. This concept is fundamental because it ensures that the compositions make sense and can be performed without any issues. So, in summary, always check the range of the first function and the domain of the second to determine if the composition exists. And that brings us to the end of our presentation. Now, let's quickly review the key takeaway. We established that the function f is 1-to-1. This conclusion is based on the fact that when analyzing the conditions, we rejected the case where both x and y are positive real numbers. From there, we deduced that either x minus y equals 0 or x plus y equals negative 2/3. Next, we looked at the equation involving these terms. X, y, 9x plus 9y plus 6 equals 0. Simplifying this, we arrived at 9 times the sum of x and y times x minus y, plus 6 times x minus y, equals 0. When further simplified, this gives us 9x squared plus 6x minus 5 equals 9y squared plus 6y minus 5. Now, this is a crucial point because it shows that f(x) equals f(y), which is essential for establishing that the function is 1-to-1. By demonstrating this, we confirm that for any x and y, if f(x) equals f, y then must equal y. In the example section, we would typically illustrate this with specific values, but the main idea here is that the function's behavior is consistent and predictable, reinforcing its 1-to-1 nature. So, in summary, through these algebraic steps and logical deductions, we've shown that our function is indeed 1-to-1, which is a vital property for many mathematical contexts. Thank you for following along.